Hello, and welcome to a new edition of H.E.L Explains with your host, Dr. Mario Thomas Rodrigo. And today we're going to be talking about semiconductors. If you're actually watching these videos we speak on your phone, or in your laptop, or on your PC, is because of these materials. So, how can a material be insulating and conducting at the same time? Well, it's not exactly like that. But because of the electronic structure of the atoms of semiconductors, what happens is that under certain conditions, the structure of these atoms will change, favoring the conduction of electricity. How does this happen? Electrons in the atoms can sit in one of two bands. They can either be on the valence band or on the conduction band. The only electrons that can travel to produce this electrical current are the ones that are sitting on the valence band. However, in semiconductors, what can happen is somehow the electrons that are sitting on the valence band can be promoted. They can jump to this valence band, and therefore when this happens is when the material is going to conduct electricity. The energy that these electrons on the valence band need to be promoted to the conduction band is what is going to determine the energy that we need to supply to semiconductor to become a conductor. Also, what will happen is if we have the electron jumping from the valence band into the conduction band, there is going to be an electronic vacuum. It's going to be a hole there. This hole will need to be replaced and replenished by other electrons, and therefore these electrons will also be able to conduct the electricity. We have mentioned about the elements on the metalloid staircase on the periodic table, but these are not the only semiconductors materials that we have. And actually we can also create semiconductors. So there are two types of semiconductors, and then you have the first type that are going to be intrinsic semiconductors that have the natural capacity of being semiconductors. But also we have some insulating materials that we can add certain atoms to, and is going to modify the electronical capacity, making them semiconductors. These atoms that we are going to supply to the material can come in one of two flavors, and what they're going to do is they're going to be supplying mobile electrons. So it can supply either electrons that are going to be the negative charge, so this type of dopant is known as N-type semiconductor, or the other option is that they're going to be supplying holes, and in this case we are talking about P-type semiconductors. So what kind of applications do semiconductors have? When I introduced this video, I said that if you're able to watch this, it's because of thanks to semiconductors. And probably the material that the semiconductors that are providing you the capacity to watch this video is going to be silicon. And silicon is great. Silicon is the second most abundant element on Earth. So it's everywhere. It's part of sand. And it has these semiconductor capabilities that are going to be so useful for us. So for example, the microchips that are part of your phone, of your laptop, of your PC are actually probably made of this material. And we have two types of microchips. We can either have like logic chips, or we can have memory chips. The second application I want to highlight is transistors. And similarly to what happened with microchips, transistors are also quite prevalent around us. Transistors are characterized by a very interesting structure. So they are structured like a sandwich, in which are going to have two semiconductors of the same type, so either 2p or 2n, and then a third semiconductor is going to sit in the middle. It's going to be the opposite. So if you have two p semiconductors, instead one is going to be n, and the other way around. What happened is then we are going to have these three semiconductors, and if by any chance the semiconductor in the middle changes, then there's going to be a massive flux of electrical current through our transistors. So transistors have great applications and they are quite prevalent, as I said before. One of the best ones that are known for is to amplify weak electrical signals. So we have our transistor, we are going to expose it to this weak electrical signal, and then the internal layer is going to change, and therefore is going to increase the electrical current that is going to go through. And as a curiosity, you know that I'm Spanish, so older people still nowadays call radios transistors, and I never understood why until I discovered transistors and semiconductors. Another application that is becoming more and more prevalent, and thankfully, because we are moving towards a greener kind of society, is photovoltaic cells. In this case, we're going to have our semiconductor that is going to be layered on a surface. The semiconductor then is going to be exposed to solar light. And what happens with this sunlight is that the photons have also the capacity to activate electrons, making them move from our valence band into our conduction band. When this happens, a hole is going to be created that is going to withdraw electrons from other atoms, and therefore is going to generate an electrical current that then we can harvest, we can harness, and we can accumulate for when we need it. And if photovoltaic cells are designed to absorb light, we are going to have LEDs that are going to be doing the opposite. LEDs stand for light emitting diode, and what they are is two semiconductors next to each other. We are going to have an N-type and a P-type. If we supply an electrical current to the N-type semiconductor, the electrons are going to move, they're going to displace, and they're going to travel towards the P-type semiconductor. At the same time, the holes that these electrons are leaving on our first semiconductor are going to be moving the electrons from the P-type semiconductor. The consequence of this is that if we are supplying even very little energy, we are going to get a massive movement of electrons within this LED, and therefore we are going to be producing a lot of light. This is the reason why LEDs nowadays have basically replaced traditional bulbs like incandescent or fluorescent bulbs in the streets, in homes, in vehicles. The materials that are going to form our LED are going to determine what kind of wavelength we are emitting, and therefore the light of our LEDs. I think that the three take-home messages from this video that I want you to take with you is, first of all, semiconductors are everywhere. They are constant in our lives and we need them. Secondly, semiconductors have somehow capacity to conduct electricity that lies between a conductor and an insulator, and is going to depend on the electrons that we have in our valence band and in our conducting band. And third, semiconductors have so many applications, and we need to carry on doing research of them, innovating them to make us more efficient and also making us less reliable on resources. And that's it. That is all from me. My name is Dr. Mario Torres Rodrigo, and I am the applications leader at H.E.L. So if you have any comments, if you have any questions, please reach out to us. Thank you very much.